Hello everyone, and welcome to section 7.5, Properties of Logarithms. Now recall, logs are exponents. So some of these rules that we're going to be talking about deal with that idea, and that's sort of why we might add something or subtract something, because it's based off of those exponent rules. So, for all of these, our base is not equal to 1, and our base and our argument are all positive numbers. So, our product property, if we have the log of some sort of product, another way we can potentially rewrite it is the sum of each of those separate logs. Now I can go from one to the other too. So if I had the sum, I could rewrite it as the product, whatever is most beneficial to me at the time. Quotient property, if we are dividing our arguments, remember, logs are exponents, so we are subtracting the log of each of those individual arguments. In our power property, this is the only one that doesn't really mirror something from the exponent rules. If I have something to an exponent, my property is that I can just bring it out in front. And you can try this with various logarithms on your calculator that are in the base of 10. For example, if I was looking at like the log of 100, that's like log of 10 squared, which would equal the same thing as 2 log of 10. Log of 10 is just 1, since 10 to the first power is 10. So 2 times 1. And then here, if I've got 10 squared, well, the power of 10 that gives me 10 squared is 2. So it does work out, and it's not just with the common logs, it's with every other type of log too. So the way we might use these properties occasionally is we might be given approximations for various logs, and then we will use these properties to evaluate the logarithm based off of the information given. So if I was told the log base of 6 of 5 was approximately 0.898, the log base of 6 of 8 was approximately 1.161. Each of these 4 problems is some sort of manipulation between 5 and 8. Maybe both, maybe one. I'm looking at the first one and I see it's pretty obvious that all I did was divide. So to rewrite it, I will take the log base 6 of 5, which is approximately 0.898, and I will subtract the log base 6 of 8, which gives me negative 0.263. We will look at what's called the change of base formula later on, where you can actually verify this with your calculator to see that your approximation is actually within reason. But you could also, for now, if you wanted to check, take your base, take it to the exponent that you just found, and see that you get approximately 5/8. Let's take a look at our next one. So I'm looking at 40, and I'm thinking, how can I get to 40 with using 5 and 8? Well, 5 times 8 is 40, so multiplication goes with addition. So if I take my logs and add them, I get 2.059, and that is, once we look at the change of base formula later on, actually approximately what log base 6 of 40 is. Or like I said, you could take 6 to the 2.059, and it will be about 40. Next one I'm looking, and I'm trying to think how I can get to 64 using 5 and 8. And though I'm not using a 5, I do know that 64 is 8 squared, so I could rewrite it as 2 log base 6 of 8, because remember the exponent drops down in front. So 2 times my log base 6 of 8 gets me 2.322. And the last one, log base 6 of 200. A little bit less intuitive, but 200 is 25 times 8, and 25 is 5 squared. So, break apart the exponent piece, put the 2 out in front, so 2 times my log base of 6 of 5, and then multiplying leads to adding, and that gets me a total of 2.957. And that's how I use my properties to approximate other logs. Now, using these properties again, it is helpful to be able to rewrite it and write logs as a single log so long as they have the same base. Notice all of these have a base of 10, since it's the common log. So I can look at each thing that's going on individually. That plus sign tells me that I'm multiplying my two numbers. That 2 I know is going to go as an exponent, and that minus sign I know is going to be a division for me. So I write out one log with whatever base it is, and like I said, in this case it is 10, so it's understood, we don't need that 10 there. I've got 8 times 5 squared divided by log base 10 of 10. So, combine any sort of numbers that I can. 8 times 5 squared, we actually just saw that is 200, over 10. That simplifies even further, and I have log of 20. So I went from having 3 separate logs to having one single one. The reason that I did this was because when I have problems like this, and I'm actually solving equations, it can really help me out. So I know that if I have a single log on either side, that I can set my arguments equal to each other if my bases are the same. All of these are a base of 2, so if I rewrite the left-hand side as a single logarithm, that's my exponent, I can pretty easily solve. X to the 4th, remember minus is like division, equals log base 2 of 125. Log bases are the same, so my arguments must be equal. Solve like normal. So x equals, technically, since we are solving an equation, we do have to take care of the positive and the negative. So it would be positive or negative 5. However, I want to make sure I do not have a negative argument. And since that negative 5 would give me a negative argument, my answer is just 5. And a word problem. So I'm looking at this, and I do have a division, so I can rewrite that as a subtraction. I'm given a pH value, so I can plug that in. So 5.5 equals log 1 over my hydrogen ions. Like I said, division I can rewrite as subtraction, so 5.5 equals log of 1 minus the log of my hydrogen ions. Log of 1, what power of 10 gets me 1? What power of anything gets me 1 is just 0. So really I just have 5.5 equals negative log of h. So if I divide both sides by negative 1, we got negative 5.5 equals log of my hydrogen ions. Now, it'd be nice to actually have an answer. So at this point, since we feel a little bit stuck, let's rewrite it and see what we get. So remember, if there's nothing here, it's understood 10. So 10 to my exponent equals my hydrogen ions. And that is approximately 0.000032. Either one of these is fine by me. I wouldn't blame you if you just left it like that. But that is how we can use this and use these properties to solve other types of problems. Using these properties, even though they are just mostly manipulations of the exponent properties, does take a little bit of getting used to. So we'll look at a couple more examples in class, and then you'll have some time to practice on your own and kind of get a feel for them. See you then.